All right, welcome back. It's week 5 of Computer Science 1 CSCE 155E. And remember that the in-person attendance policy has been updated, so we've got 53 available seats. The more I open it up, the fewer people show up. So good or bad, I don't know. I'm going to choose to interpret that as my live streams are just so awesome that nobody thinks that they need to attend. So that's how I'll choose to interpret that. Last week we started covering functions, and what we did at the very end of last time, let me make sure that our audio is working here fine. Yep, good. All right, at the very end, what we did is we modularized our code. What we did was we took our prototypes and we put them into a header file. And we took our definitions and we put those into a source file of the same name, but with a .c after the end. And this is typically how you do this. And this is why when you include a library, you include math.h. You include stdi.h. You're only including the header file because literally what is happening is the preprocessor, remember there's a hash include, the preprocessor is going through and grabbing all of those prototypes, cutting and pasting them into your code so that the compiler is aware that there is this function out there called round, that there is this function out there called, for example, in our demo here, round to sense, or there is this function out there that's called round to digit. Remember that we did keep all of our documentation, our doc-style comments here. We put all those in with the prototypes in the header file. Over here in the C file, we actually had all of our definitions. One other thing that we did was we included that header file, but instead of using the Langle-Wrangle convention, we used the double quotes convention. And that's just simply because with user-defined libraries, you use the double quotes instead. You can use the Langle-Wrangle, but it's the convention to use double quotes. The only difference here is, if you really want to know, is where it looks first. So if it's Langle-Wrangle, it'll look in the standard libraries first. If it doesn't find it there, then it'll look in the current working directory or wherever the user-defined libraries are. If you use a double quote here, it says, this is a user-defined library. Don't even bother looking at the standard libraries. Just look in the current working directory or wherever else I happen to store my stuff. And so it's usual to see the double quotes for user-defined libraries like this instead. All right? We moved our definitions to a file named round.c. In round.c, we used include, include round.h, right? To include the prototypes. Uh-oh. There we go. It's saved now. All right. What else did we do? How did we compile everything? And that's what I want to review right now. Over here, we have all these files. We have demo.c that uses our function, right? $188.73.5, and we want to call this round to sense and print it out. Well, if I just try to compile demo.c, of course it's saying I have no idea what round to sense is. Just like if we tried to compile this without -lm and we used a math library function like round instead, it would say the exact same thing. In fact, let's try that. Round, and if not use the -lm, it's going to say undefined reference to round. It's a library. You have to link it in, right? In some way. Now, the way that you do this is you have to compile it first. Right now, this is just source code. It's high-level code that's readable by a human, but it's not executable by a computer. So what we need to do is we need to compile it, round.c. Right? And when we do that, you'll see that there's this new file over here called round.o. That's the object file, round.o. It's a binary. I won't even be able to open it up in this IDE because it's just a bunch of binary. But that is this file that has now been compiled into machine code so that it can now be linked into something that's executable. By itself, this library is not executable because there is no main function. You have to have a main function in order for something to actually run on your system. So, how did we compile everything? We compiled our library using gcc-c to compile round.c, right? Which produced a round.o object file. Now, to compile an executable, what did we do? Right now that we have these files all together, I can go gcc demo.c, or actually I want to include the round.o file. The order doesn't really matter, but we'll go ahead and do it properly like this. This is basically taking the place of that -lm. Instead of linking in the math library, I want to link in this, this round.o file. Now, in the round.o file, we did use the math library here. We used round and pow. So what else do we need to link in? We also need to link in the math library. I will copy paste this so that we have it, and when we do that, you see that there's this a.out file that has now been produced, right? So when I run it, a.out, now $188.73.5 rounds to $189 and no cents. There's something wrong there, right? Oh, what was wrong? I was an idiot and I just changed this to for demonstration purposes. 2 cents. There we go. Let's do that again. Note here I do not have to recompile the library because I didn't make any changes over here to round.c or round.o. I only made changes over here to demo.c. Right? Oops. Well, now I did. There. So do that again, and we get the correct expected behavior. It rounds up to the nearest cent. Okay? So we compiled into an executable using gcc round.o demo.c, and then of course -lm. That's just because of CS50. Your mileage may vary there depending on your setup of GCC. You may or may not have to use that -lm. All right? Okay. So that was a review of how we brought everything together. An advanced topic would be make files. Oops. Make files. Right, there we go. So this can get very, very complicated very, very quickly. Even if you only have like say 2 or 3 files, library files that you've separated out, compiling everything together and defining dependencies that, well, this file uses this library, therefore this library has to be compiled before this library can be compiled, right? Defining all those dependencies, you can use another programming language called make, and you'll see that this week in your lab. We've already made the make file for you. You can go ahead and take a look at it and reverse engineer it if you want. You can take a look at see how it operates. We won't get into that directly in this course, but of course there are tutorials about it, and one of the advanced topics in one of the labs is a tutorial that you can read about it and then create your own make files. But if you want to, otherwise you could just take the make files that we have, reverse engineer them so that you don't have to type all this stuff every single time. Generally, once you've got your make file created, all you have to do is type make. And of course, it's not going to work here because I don't have a make file. There's no target specified and there's no make file, so it's not going to work. Right? But an advanced topic, it's not that advanced, it's just another language. It's a build language, okay? One last miscellaneous item, is that we need to talk about the void keyword. The void keyword can be used to specify that a function does not take any, does not return any values, right? Generally, a void function in a void function, you still have a return statement, but with no value returned, right? It's just good practice to keep that return statement there. And again, if you want to see an example here, if I have a void function, void, right, that's the return type, foo, and do whatever you're going to do in this function. Do something. I don't know what you would do in this function, but you can have void functions that don't return anything. Also note, as we've already talked about, you can have functions that don't take any input either. You can go ahead and use the void keyword here, but it looks weird. It's not usual, and I would recommend not doing it. This is better practice here. Right? But if you do have a return type that's nothing, you don't just put nothing because that's actually going to be a different thing. It actually by default returns an integer, and you don't want to do that. You want to use the void keyword if you're actually not going to return anything. Right? Okay. All right, so a little bit more advanced now. Let's talk about how do functions actually work. I've shown you how to write functions. I've shown you how to use functions. And we've gone a little bit over general design principles. For example, if you ever find yourself using the same piece of code more than once, huge red flag. Put that into a function. Reuse the function. Don't copy pasta code every time you need it. Now, this is a general guideline, not a hard and fast rule. There are some instances in which I would prefer to copy-paste code, but those instances are very limited and probably not applicable to anything that you're going to do in this course. So every time you find yourself, doing the same thing over and over again, not inside of a loop, I mean, but like doing it up here and doing it over there and doing it over there, then that's a huge red flag that you should design a function to do it. Okay? But how do functions actually work? Programs have what is called a program stack. Right? It is a LIFO, that is last in, first out data structure. Right? So what does that mean? Well, what is a stack in real life? Think about a stack of dishes, right? It's an organized pile of dishes. Right? Now, how do you interact with that pile of dishes? You want a dish, so you go to the cafeteria. You want a dish. Do you take the dish at the bottom of the pile? No. You take the dish at the top of the pile. Now, say that you've washed the dishes. Where do you put that new dish onto the pile? Do you put it somewhere in the middle of the pile or at the bottom of the pile? No, it's going to fall over and break all the dishes. Where do you put it? You put it at the top. So that the last dish that you put at the top is the first one that comes off when you when you need a new dish, right? So that's what we call a last in, first out data structure, a LIFO data structure. You interact with items on a stack at the top of the stack. All right? The operation that you can put things on top of the stack, you put things on top of the stack by pushing them onto the top of the stack. Right? You pull things off, you retrieve things from the top of the stack by popping them off the top of the stack. Right? This is not updating fast enough, so let me go ahead and close this for a second. I will put it back up in 1 second here. Bear with me. Now it should be a live update instead of me having to save it every 2 seconds. There we go. Zoom in a little bit more. There. All right, that should work a little bit better. There. So how does this help us with functions? All right. I should add that there is no middle retrieval or insertion allowed, right? So how does this help us with respect to functions? Every time a function is called, a new stack frame is created and placed on top of the call stack or program stack. Right? So both of those things are going to be interchangeable, a call stack or a program stack. Right? All local variables and all parameter variables are allocated and exist inside each stack frame. So one of the questions last week was, how can you have a variable name, say, x, in function A, and another variable name with the exact same variable name, x, in function B? Which is what we did when we used this round function. We had a variable called result here, and another variable called result here. The same variable, but in different scopes, in different functions, and that's because they exist in different functions. They exist in different stack frames. Right? Every time you call a function, a brand new stack frame is created with which contains all of the local variables and parameter variables for that function. Right? When a function is done executing, its stack frame is popped off the top, returning to the last called function. So now you can see how this helps us, how this LIFO data structure helps us. Because if function A calls function B calls function C, what we have is a stack of breadcrumbs that we know where we've been. We went from function A to function B to function C to function D. Well, how do we go back? How do we return? We can return by popping each one of these off the stack, pop the one for D off the stack, and we're back at C. Pop the one for C off the stack, and we're back at B, right? We call these breadcrumbs for a very good reason, because it is how you can, it comes from the story of Hansel and Gretel, right? Hansel and Gretel go into the forest, and they need to find their way home. They don't want to get lost, so what do? They start leaving breadcrumbs behind them for when they came. Now, the breadcrumbs got eaten, but if it had worked, how would they have gotten home? They would have just looked behind them, saw all the breadcrumbs, and they could go back the way that they came. That's exactly how stack frames work. For example, here's some code. Let me cut and paste this code right here. Right, there we go. C code. There we go. So here's some code. It's directly from the book. And that is my book, not the Xi books. But I've conveniently called each one of these a different name. So this is terrible code. I will admit this is terrible code because you would never do something like this. If you want to compute the average of two numbers, you just do it. You don't create a sum function and an average function here. Right? I don't know why it's not showing up correctly for that, but whatever. All right, ignore that. Those includes are there. I'm not sure why they're not showing up. But in any case, let's look at what this program does. We create two variables called n and m, and another variable called average that calls this function average, AVE, and it calls this function average, passing these two variables in as inputs. When this function takes over, those are not n and m anymore. Now they are a and b. Right? Those are two brand new variables that have been created on the averages stack frame. Right? And then what it does is it calls another function, passing those in, and it creates another stack frame on top of that. Here's the visualization. Let me go ahead and zoom in if I can. Zoom in. There we go. So when a program actually starts, well, a bunch of other stuff actually happens. You've got the program code. You've got global variables and static content and stuff like that. And then you've got main is called first, right? When main is called, remember those local variables are created, n, m, and average, and those exist inside of this stack frame right here. We'll ignore this for a second here, but we've also got arguments, argc and argv. Remember that you still have arguments to the main, which is argc. Those are command line arguments. They're stored in the stack frame for the main. When main calls average, a brand new stack frame is created here. You've got local variables, in this case y. We only created one local variable so that we could return it. And of course, the arguments, a and b. A and b are not the same thing as n and m because they exist in completely different stack frames. Likewise, this a and b is not the same thing as the a and b in sum because a new stack frame is created with new parameter variables. Right? And then, of course, unused stack space. We'll talk about this later on, but what happens if, we'll talk about this in the context of recursion, but what happens, do you think, if function calls function, calls function, calls function, calls function, you just stack way too many dishes? What eventually happens if you've got a very, very tall stack? They fall over and break. And in the context of computing, since this is a stack and it's full, we put one more dish on it, and it's overfull. So what happens is overflow, and it's called a stack overflow. Sound familiar? It's the website, Stack Overflow. That's where it gets its name. Right? And so it is actually a risk for your program. I believe usually on modern systems, you've got a stack of size like 4 megabytes or something like that. If you're on an embedded system, of course, it's going to be much lower, several hundred K or something like that. If you go back 50 years, you might only have a few hundred K. So you have to be very, very careful about that stack space, depending on where you are. For the most part, you don't have to be that careful because you've got a full 4 megabytes to work with there. But in any case, you do have each one of these stack frames. Now what I'm going to do is I'm going to take this code and I'm going to visualize it for you further. This is another tool that I use, especially in the pre-prepared videos. It's called Python Tutor, but it has support for C. And we're just going to visualize the execution of this program. Now, our stacks grow up, but really, if I take my computer and put it upside down, it's not a stack of dishes that's going to fall over because of gravity. It's just a way to visualize something. Stacks grow up. In this case, because of the way that they've set this up, it's going to grow down. So I'm going to go ahead and execute this. First of all, we'll go ahead and initialize nm and go on to the next one here. But before I do that, we'll look here. There's argc. There's only one argument. They use a poop emoji here to show uninitialized memory space. Garbage pointers. We'll get to pointers by the end of the day here. Then we've initialized n here to 10. That was line 15. We'll go ahead and go and initialize m, and that's been initialized. This entire thing, this blue thing right here, is main's stack frame. All right? And then finally, we want to compute average. So what do? We end up calling this function, and guess what happens? A brand new stack frame is created on top of the stack, but again, now we're growing downward. So just take your monitor at home and flip it upside down so that it's growing the proper way. Don't do that. Or if you've got one of those fancy monitors, you could always, flip it. The gaming monitors that you can flip, I don't know if any of them go 360 or not, but certainly you can try. Don't try. All right, so anyway, we've created a new stack frame here, and you'll note here that A and B are both completely different variables than n and m, right? Because they exist in a different stack frame. They receive these values, 10 and 16, right, when this function is called. Now we're going to call another function here, sum, to sum them up. So we've got yet another stack frame with a, b, and x. X is going to be the return, the temporary variable here that is local to the function. So when it receives 10 and 16, x receives the value of 26, and when it returns, what happens to that stack frame on the top of the stack? It gets popped off. And, oh, there we go. There, now we're at the end of the function. And there, it's gone. How did we return? Well, all we have to do is look at the next stack frame once we've taken this one off the top, the next dish. Right? The next dish has everything that we left on it, 10, 16, and now it receives the value 13 because we've divided that by 2 here. Right? And then when we get to the end of that function, the stack frame is, again, popped off, and now we're back at the main. It prints out. There's the output there, the average of, well, 10 and 16 is indeed 13. And then we are done with the program. Right? Now, the main, I don't know if that stack frame ever gets popped off technically. It doesn't really matter because at the when our program is done executing, all of this stuff is cleared out by the operating system anyway. Right? It takes care of deallocating all that memory that the program allocated. Right? So that's how functions actually work. And that's why we can have local variables of the same name in different scopes, in different functions. Okay. All right. I'm going to go ahead and get rid of this since it's in the book and it's not that. Do not ever write code like that. That was just for demonstration purposes. All right. So another aspect of how are parameters passed to functions. Right? Right? By default, variable values are passed by value to functions in C. Right? What this means is when a function is called, the values stored in a variable are passed to the function. The variables themselves are not passed to the function. Right? Therefore, you basically have two different variables with the same value when you initially call a function. Right? And one way to think about this is that when a function is called, copies of the variable's values are passed to the function, not the variables themselves. As a consequence, any changes to variables in a function that are passed by a value are not apparent or seen by the calling function. Right? What I mean by that is, let's consider the following piece of code here. Right? What I want to do is I want to write a function, and here I'm going to go back to the Python tutor and get rid of this stuff. There we go. I'm going to write a function here to swap two variables, a and b. A and b, they'll simply be swapped. Okay? Now I'm going to write a different main here because I'm no longer computing the average. Okay? There we go. All right. All we're doing here is we have x and y, which are 10 and 20. We print those out, so we would expect that to be 10, 20. We call this swap function on x and y, which receives them as a and b. It stores a into a temporary variable, places b back into a, and then takes the temporary variable and places it over here in b. Right? And then we return. In fact, I'm going to add another print statement here to show you that indeed this code right here is working. Right? Let me make sure that we're all in frame here. Yeah, we're in frame. Okay, good. So not printing x and y, I'll print a and b and a and b. All right? Now, is this going to work? When I come back from this function, will x and y be exchanged? Let's visualize this execution here. It shouldn't take up to 10 seconds. There we go. All right. So we're going to go ahead and go through this code a little bit quick. There we go. So I went through the first three lines here, 10 and 20, and of course x and y have the values 10 and 20 because that's what's stored in these two variables. But when I call this function, a and b receive the values 10 and 20, which is normal. Now when I go and swap them, so I'll go fast forward through the next three steps here. It's creating a temporary variable that receives 10, 20 will go into a, and then 10 will go back into b. Right. Oops, did I do that? Yeah. Oh, you know what? This is bad code. Let me go ahead and edit this code, sorry. So what did I do wrong? B should get the temporary variable's value. Let's visualize that again, sorry. And this time I'll fast forward. We'll see that x and y have 10 and 20 printed out, and we have 10 and 20. When I call this function, 10 and 20 are received. I put 10 into the temporary variable, 20 into a, and the temporary variable back into b, so now they're swapped, right? In fact, when I print them out, you can even see that they're swapped, 10 and 20. But when I return back from the function, before I return back from the function, do you see that x and y are changed? No. Why? Because they're completely different variables. Those are the original variables. In swap, we received copies of those variables called a and b. We swapped the copies. We didn't swap the original. So when we go ahead and go back to the main function and print them out again, we see that in fact 10 and 20 are not swapped because they never were swapped. We never touched them. We only touched a and b in this function up here. All right? So as a consequence, when things are passed by value, only copies of them are passed to the function. So suppose I really wanted to write a function to change the original values of the original or the values, I should say, of the original variables. Right? I do want a proper swap function. All right. What we're going to need to do is we're going to need to create functions that are passed by reference. We need to create functions that pass the variables, or more accurately, or references to the variables, so they can be manipulated, changed basically, right? To do this, we need to create functions that are pass by reference. There we go. Right. However, to do this, we need another new concept called pointers. To do this, we need to talk about pointers. Right. This is something that's almost unique in C, pointers in C, okay? This is something that not a lot of programming languages allow you to do because they try to abstract away these details. Pointers in C basically allow you to manipulate individual memory cells directly in the computer. A lot of programming languages don't allow you to do that. In fact, a lot of programming languages like Java, they have a virtual machine. They don't even let you have access to the actual metal memory addresses. Instead, they're virtual memory addresses that are run on a virtual machine, like in Java. Some questions online here. When do we use void functions? So this goes back a little way. I should have checked it. You use void functions whenever you want to create a function that doesn't return anything. I can't give you any good examples at this point, but one example would be, say, printing out a welcome message, right? And you want to put this very, very long welcome message into a function so that you don't have to put it in your main mess up your code. Go ahead and put that into a void function, call it so that it prints, and then come back, and you don't expect anything back from that function. But otherwise, in the future, there might be some other use cases for void functions. Okay, but in general, void functions are not very useful, so consequently, they're also not very common either. Right? Okay. All right. All right, again, if you're on Piazza and you have questions about like a hack or something like that, make sure that you're posting to the main section, because this is the live Q&A is for stuff in lecture only. Okay. So let's talk about pointers in C. What I'm going to do is I'm going to go ahead and go into code mode here, and let's talk about regular old variables. Here's a regular old variable declaration. Int x is equal to 42. Right? I'm creating a variable, an integer variable called x, and I'm setting it equal to 42. Right? Now let's go ahead and create what's called a pointer variable. Create a pointer variable that can point to a memory location that contains an int value. Right? To do that, it's very, very, it's not that different, but it's a subtle little tiny difference here. Int star pointer to x. We'll call it that, okay? So the only difference is, well, same naming conventions, of course, but I'm using a star here. So anytime you create a pointer variable, you're putting a star in front of it. I don't know why they decided on a star way back when, but that's just what it happens to be. An asterisk, basically. It is an asterisk technically, but we call it the star operator, right? At this point, ptr pointer, to x does not necessarily point to anything, right? It could point to an invalid memory location, right? Remember, memory has both an address and contents. You need this so that you can say that, oh, well, I need everything in a computer needs to be stored in memory, right? Well, how do you access where your program exists? How do you access where a variable exists? In memory, you've got an address and then the actual contents in memory. And that address is something that is how you look things up. Variable x, where is that stored in memory? Well, the compiler knows, the system knows, and its memory address is right here. So it can go to that address, and then it can look up the value. Right? It's just like houses. Where do I live? Well, I have an address, right? And to look me up, you can go ahead and go to that address. Where does Jane live? Well, she's got an address, and we can look her up and go to her address and find her in our house, right? And just like memory, where does the variable x live? Well, it has a certain address, and that's where it lives in the computer. That's where it lives in memory. So a pointer allows you to point not to a value in memory, but instead to the memory address itself. Okay, and I've got some visualizations in the book, but unfortunately, let's see, do I have them up? let me go ahead and just grab that really quick if I can. This is my book. This is not Zybooks. But I'm sure that Zybooks has something very similar. So here's an example. You've got an address and then the contents. So if you've got if you've got an integer variable that's set to 10, then its address is some hexadecimal code that we don't really care about. Just like you don't really care about the addresses on a house. It's a way of organizing street addresses. Well, this is a way of organizing memory, right? It is contiguous, so it goes up 84 up to 88, up to 80, 84, 88. Just like in on a block, you would go to 1057, then 1059, then 1050 or 61, right? And on the other side, there would be all the even addresses. It's just a way of organizing things. The actual values here, like 42 or 10, are stored as the contents of memory, whereas the address of the variable, well, that's going to be some hexadecimal code that we may or may not care about, right? In fact, I'll show you. Let me go ahead and edit this code. I'll go ahead and get rid of this. And printf x has the value %d and is stored at memory location %. Now here is a way that you can get the memory location printed in a nicely formatted manner. P. What do you think P stands for? What are we talking about? We're talking about pointers. So it will print out the pointer memory address of X. Ignore this for a second, although it looks familiar. Right? Ampersand, where have we seen that before? Scanf, exactly. And now we're about to learn why that is. So I'm going to go ahead and replace X with Y and Y here. Right? And I will go ahead and compile this and visualize the execution here in a second. Or we could have done this on CS50 as well. It'll work there as well. We'll create X and Y, and then we'll print, and we'll take a look at what that looks like. X has the value 10, Y has the value 20, as expected, and they're stored at memory locations, whatever this is, and whatever this is. They're very, very close in hexadecimal 8 versus C. I think that's going to be like 64 bits away, or 8 bytes away, or something like that. I can go ahead and run this again in the CS50 IDE here. Yeah, okay, I'll go ahead and get rid of this. Right, there we go. And gcc demo.c. And I'll run it again. Oops. What's wrong? Why aren't you printing? gcc demo.c. Huh, okay. Weird. Oh, duh. There we go. And what's wrong now? Oh, I cut and pasted a lot that I shouldn't have. Let's get rid of all this stuff. There we go. There we go. And run that. All right. It has the value 10 and it's stored at this memory location. Value 20 and it's stored at this memory location. These are only 4 bytes away. For every value here, that's a byte. So this is byte addressable memory. Here's the first byte, the second byte, the third byte. Every byte has its own memory address. If I run this again, would you expect it to have the same values or not? I don't know. Let's find out. Completely different values. Every single time I run this, completely different values. They're always 4 bytes away from each other. There's only a difference of 0 to 4 here. Why is it different every single time? Because my program loads up its stack in a different memory location every single time it runs. The operating system is doing that for me, right? So it's going to be very, very unlikely that you will ever get the same memory location. If you do get the same memory location, then that's probably the operating system reusing stuff. But other programs are running all the time, taking memory, allocating memory, deallocating memory. So you're never going to get the same one twice. And if you do, then you're either very, very lucky or very, very unlucky. I don't know. Go buy a lottery ticket either way, right? Couldn't hurt. Don't gamble. Anyway, so it could point to an invalid memory, but if you don't have it pointing to anything yet, it could point to an invalid memory location. It could point to a valid memory location that doesn't belong to you, or it could point to a valid memory location that does belong to you, but you still shouldn't do anything with it. Why? It's okay to screw up your own memory as far as the operating system is concerned. It's okay as far as the operating system is concerned, the OS is concerned, to screw up your own memory. Hey, it's your memory. The operating system gave it to you. You can do with it whatever you want. If you want to screw it up and destroy your own program and corrupt your own memory and corrupt your own program, that's your business. Remember, C is a language that if you want to shoot yourself in the foot, it's simply going to ask you what caliber do you want. It's not going to say, are you sure you want to do that? Right? It's going to say, go ahead. I'll let you do that all you want. All right? So right now, this pointer is not pointing to anything necessarily correct. Right? So what do we need to do is initialize it. The above is what is known as an uninitialized pointer. Right? You don't want this. Right? So it is best practice to make pointers point to something, or failing that, at least point to null. Null is another concept of nothing. So far, we've gotten a lot of concepts of nothing, right? 0 is nothing. Void is nothing because this is a function that doesn't return anything. Null now is a pointer nothing. It is all caps. It is case sensitive. It is defined in the standard library. So you do need to bring in the standard stdlib to define it. Usually it's defined as 0, but not always. At the binary level, it might be something different. So don't just use 0 for null. Use null for null. Right? 0 is a different kind of nothing. 0 is numerical nothing. Null is a memory nothing, and they're not the same thing. You shouldn't treat them as the same thing. Okay? So what does that look like? Let's go ahead and go back into code mode here. So you can create and initialize it to null. As I did before, I will take int pointer to x, and I will set it immediately to null. Okay. Later on, you can make it point to an actual variable. All right. To do so, you use the referencing operator, right, which is the ampersand. And as you already noted, that's we've seen this before in scanf. The ampersand basically gives you the memory address of the variable. So I'm going to make pointer to x point to x. And the way that I'm going to do that is pointer to x is equal to ampersand x. Okay? Now, the ampersand is the referencing operator. Right? It gives you the memory location, that is address, of the variable you attach it to. Right? So x is the regular old variable, and ampersand x is the memory address of x. Cool. You can get direct memory access using C. Right? With great power comes great responsibility. If you are directly accessing memory, you need to make sure that you're not corrupting memory. If you do, then bad things will happen. Right? So you need to make sure you are not accessing or illegally accessing memory or accessing invalid memory. Right? You could have memory addresses are usually all positive, right? Or they're in a certain range. Memory addresses say start at 0 and go up to, if you've got I don't know how many megs are standard nowadays. If you bought a computer, laptop computer, 8 gigs of memory, 8 gigs. 16 is usual now. Okay, so 16 gigs. If you try to access something beyond that, of course, there's virtual memory or like a negative value, then that may not necessarily exist. And if it doesn't exist, the operating system is going to say, wait a second, that's an illegal memory access error, or that memory doesn't belong to you. Imagine if you could access arbitrary amounts of memory. There's a program over there that has passwords or system passwords or something like that that is being run by the operating system. Imagine if we were able to write a small program to simply access the memory of that program over there. We could get passwords, and that's exactly how a lot of buffer overflow attacks work. Right? So you don't want to do that, right? If you do, then it could lead to and you've seen this before, segmentation fault. A segment is a segment of memory, and a segmentation fault is an illegal access of that segment of memory. And that's why if you forgot the ampersand when you used a printf, that's why it killed your program, segmentation fault. Or it's why if you try to access a variable that doesn't exist, like argv, the argument vector that's given as command line arguments, if you're expecting 3 command line arguments and they only give you 1, well, that third one doesn't exist. So trying to access it's going to lead to a segmentation fault. I'll show you. So let's go ahead and try to access a memory location that doesn't belong to us. Int star pointer to x. I won't set it equal to null here. Let me set it equal to 10. Right? This illegally makes the pointer point to memory address 10. I have no idea if that address even exists, but it certainly probably doesn't belong to me. It's such a small memory address that it probably doesn't belong to me at all, if it exists at all. So what I'm going to do is I'm going to try to access it. Printf pointer to x now points to memory location %p and contains the value. Let me go ahead and put this onto 2 lines so that we can see it all. Pointer to x. There we go. Printf. And contains the value %d. And the line, ignore this for 1 second. We're going to get to it in a second. Pointer to x. Right. There we go. Now let's try to do that. Good. It's just a warning though, right? So if you have your WAL flag set, it's going to catch things like this, right? And it's going to say, nah, you can't do that. Or you probably don't want to do that. But it's just going to be a warning. Again, you want to shoot yourself in the foot, I'll warn you about it, but go ahead and do it if you really want to. Let's go ahead and try. Segmentation fault. The memory location 10 does not belong to us. So trying to access it, the operating system says, no way, you can't do that, that's illegal, kills your program with a segmentation fault. Right? So how do we properly make it point to x? With that ampersand x. Now let's go ahead and we'll save it and compile it. Right? And it's fine with this now because we're not setting it to an arbitrary memory location. When I run this, pointer to x is now pointing to x. So what value does that memory location contain? 10. And when we run this, we see that the memory location here is the same as the memory location here for x, and the value stored there, 10, is the same value as we stored in x. Right? Cool. Now we've got a way of accessing memory. Okay. So if you do, it'll lead to a segmentation fault. You can also check for null pointers. You can check for null pointers using the following. All you have to do is do an equality check. Int ptr pointer to x is equal to null. I'll go ahead and set that equal to null. You can check later on if it's null. If pointer to x is equal to null, then printf invalid null pointer, right? Or whatever error message you want. Quit out of the program, return a value or whatever. Okay. So all you have to do is check for equality with null. And again, don't treat null like 0, right? You might even see code examples that do that. Don't do that. It's a bad practice. It's a bad habit to get into. Okay. All right. So again, we already talked about it above. How do you make it point to a valid memory location? You use the ampersand, right? Once you have a pointer variable, you may need to access or modify the contents of the memory that it points to, right? In other words, you may need to change a pointer variable excuse me, into a regular variable, right? So that you can use the assignment operator, you can add it or something like that, you can do whatever you want to do with it. To change a pointer into a regular old variable, use the dereferencing operator. And surprise, surprise, that's our never introduce another thing if you can confusingly reassign something that already exists. For that, you use the star operator. Right? So that's why I was writing it like this. This is a pointer variable. Pointer to x is a pointer variable, right? Because it was declared with a star. To make a pointer variable into a regular variable, you put a star in front of it. Now this is a regular variable, and we can treat it like x, right? We can even change the values of it, right? Let's go ahead and do that. Pointer to x is equal to 42. We'll change it, the value 10 into 42, and then we'll print it out again. It still points to the same memory location, but now its value should be 42. Let's try it. Right there. It's same memory location as before, but before it contained the value 10, we changed it to a value 42. Okay? And again, it is by dereferencing that pointer. What if I just did this? Now I'm back at square one, where I set pointer to x equal to 10, and it gave me a segmentation fault. In fact, we can see that again, that it's going to give yet another segmentation fault. Of course, it's warning us about it again. Don't do that segmentation fault. You need a star in front of it to make a regular variable into a pointer variable into a regular variable star. Going back the other way, a regular variable into a pointer variable, ampersand. Star, ampersand. They're just opposites of each other. Okay? All right. Good. So now we're ready to solve the original problem. Using pointers, you can now create a function that passes values or passes variables by reference. That is, we'll pass the memory locations of variables so that the function can directly manipulate the contents of memory. How is that going to work? Let's come back over here to the visualizer here. Okay. Let me go ahead and go back to my code over here. I want this main right here. Remember, we wanted 10 and 20. Let's go ahead and create a void function here. So here's an example of where you would use a void function. I'm not going to return anything. I'm going to give you two variables by reference. You're going to swap them. I like the analogy of I'm not going to give you variable values 10 and 20. I'm going to give you two buckets. And in those buckets happen to be 10 and 20. What you're going to do with those buckets is you're going to take the values out of those buckets, swap them, put them back in the buckets, and we both know about the buckets. I've got the buckets, you've got the buckets. I'm just handing them back. Then you hand me back the buckets when you return, and I see that, oh, 10 and 20, they've been swapped. They're no longer in the same buckets anymore. Okay? Swap. Now, what we did before was int A and int B. Those are passed by value. If I want to instead pass a pointer variable, what would I put here? A star, right? And this will also be a star, right? Those are now pointers, okay? Passing A and B by reference. A and B are pointer variables, not regular old variables. Oops, that's not what I wanted. So what can I do? I can go ahead and create a temporary variable here. Int temp is equal to A is equal to B is equal to temp, just like I did before. Except that, is A a regular old variable anymore? Nope. So I can't treat it like a regular old variable anymore. If I treat it like a regular old variable, then I'm going to get a segmentation fault, undefined behavior, whatever, right? How do I take this pointer variable and make it into a regular variable so I can take out the value from the bucket and put it into this variable called temp? I dereference it, okay? Likewise, B needs to be dereferenced, dereference, dereference. Do I dereference temp? Is temp a pointer variable? Nope, it's just a regular old variable. You don't dereference regular old variables, okay? You only dereference pointer variables. Now let's go ahead and, let me go ahead and try to compile this over here in the demonstration and see what it says. Save it. There we go. All right. It doesn't like this program yet. And I wanted to show you this, this error message because it will probably come up at some point. They're all just warnings, though, right? It's complaining about this argument 1 to swap. Swap takes, argument 1 and argument 2, by the way, both of them. Swap takes 2 pointers, right? Am I giving it pointers here? Are x and y pointer variables? Nope. X and y. So you might think, okay, well, I'll go ahead and say, I'll just make them pointer variables. Can I do that? Can I make a pointer point to 10? No. That's not where you do it. Where you do it is, I want to take this regular old variable and make it into a pointer variable so that I can pass in the memory location over here. So how do I take a regular old variable and make it into a pointer variable? Just the opposite, ampersand. Ampersand. And now, the complaints should go away. Yep. And now when I actually run this, 10 and 20, or 10 and 20 since I don't have enough fingers to hold them up, now they will be swapped. Let's go ahead and run this. 10 and 20, 10 and 20, and now 20 and 10 have been swapped successfully. Again, let's go ahead and look at this from the visualization point of view. There we go. I just cut and pasted that. Let's visualize this execution. And I really like this visualizer because it really drives home the point that these are pointers, right? Let's go ahead and run through this code a little bit. 10, 20. There we go. We print those out, and of course it's just normal up here. Next, swap, right? A and B, these are pointer variables. They do not receive the values 10 and 20. They receive pointers, right? And I can't move this around, but I wish I could. But you see that A is pointing to X when I highlight it right here. There we go. When I highlight that, A is pointing to X. B is pointing to Y. So when I go down and execute this swap right here, what it's doing is it's jumping to this bucket, pulling that value out and putting it into temp. Right? It's line 9 is jumping to this bucket and putting this temporary, jumping to both of those buckets, taking those values out and then putting them into each, putting one into the other, right? So that now 10 and 20 have been swapped here, right? Because we're doing it, we're manipulating it through its memory addresses right here, okay? And when we come back, that stack frame is destroyed. The pointers are destroyed, but the original values, X and Y, are still in the stack frame of main. And they've been swapped around. Right? Magic, right? You cannot do this in most programming languages. This is something that is almost unique of C, right? There. And we're done running here. Okay? So I think most of that is in the book anyway, but if you want to, we can I can include that in the notes, right? So a summary here. Yeah, let's do a summary. Summary of pointers. Right? A pointer is a memory address. or a reference to a memory address. Right? A pointer variable can be declared using the star operator. So again, int star ptr2a, or whatever you want to call it, right? It is best to initialize pointers, or at least make them point to null, right? All caps there, right? To make a pointer variable into a regular old variable, use the what operator, and likewise the opposite, to make a regular variable into a pointer, right, or memory address, use the what. So, summary here. To make the, what's the first one? Pointer variable into a regular old variable, what do I do? Which operator? Star or ampersand? Careful. Star. Pointer variable into a regular variable, you dereference it, right? Dereference it, right? To make a regular variable into a pointer variable, you use the ampersand. This is reference it. I don't know why I highlighted those, but for emphasis, basically. Not that it's a mnemonic device that you can remember. In fact, I don't know of any mnemonic devices. If anybody can come up with a mnemonic device for remembering that stuff, I'm all ears, right? Why would I need to use pointers instead of regular variables? Because now you can manipulate things with respect to memory. That swap before, it was not possible with pass by value. But now it is possible with pass by reference, right? Not only that, but now that we have pointers, we can get into things like arrays and strings, which are, and dynamic memory, which you need pointers to do. Now that we've got pointers, the next thing we're going to do immediately with pointers is, now that we have pointers, we don't have to use our return value for anything. If I give you a bunch of input variables and an output bucket instead of an output return type, now what you can do is you can manipulate, you can use those values, compute the result, and put that result into this bucket and give me back the bucket rather than returning a value. Now that that frees up that return value, we can use that for error handling, right? And that's what we're going to do next, all right, starting on Wednesday. Let's see. What else do I want to talk about, though? Oh, okay. So overall summary. All right. Overall. Oh, sorry. Overall. I want to do a callback. Recall. We had to use scanf. Here's another example of where you would have to use pointers. %lf. And then %b, right? We had to use, in other words, we had to use the ampersand. Why? Do we understand that a little bit better now? We're passing, we're giving you the variable b's memory address. We're giving you the bucket so that you can read the standard input, take that standard input and put it into the bucket so I can have that bucket back. Because scanf does not return the parsed value. Right? It returns something else, but it returns an integer value that basically can be used for error checking. But it is passed by reference. It is only possible to do something like this if I gave you a bucket, if I gave you a pointer of scanf, I want you to read the input and put that value into this memory location over here that I know about. And it does. It reads the input, it parses the input, and it puts the value over there so that I can get it back, right? Rather than returning a value to me. And that's how scanf works. It's not like A to F. A to F takes a pre-existing value, parses it, and then gives it the result back to you. Or A to I, whatever you're going to use for that stuff. Pointers opens up the rest of the world of C. It opens up, again, arrays, strings, which are arrays basically, error handling, and a bunch of other things that we can now do because we've got pointers. Okay? All right. Good question online. Any questions inside? Face to face here? Oh, not pertaining to this. Okay. Okay. Well, that's I'm good enough for today. Okay. So actually, wait. Let's go ahead and write down what I was saying before. We had to use the ampersand. Scanf is a pass by reference function. We pass in the memory location of the variables we want the value stored in. All right. Let's see. Pointers can be used now with respect to arrays, strings, and dynamic memory, which is what we're going to get into eventually, but more immediate to the point, which we're going to start on Wednesday. We can now also write functions that return multiple values, right? And I'm putting return in quotation marks here because I'm not talking about actually returning multiple values. Instead, what we would do is we would pass in multiple variables by reference, and multiple values could be stored in those variables, right? So we can get the same effect, right? Same effect as returning multiple values, right? This also frees up the return value, right? We no longer have to return design functions, I should say, design functions to return values, right? Instead, we can do it through pointers. Instead, we can now use the return type to indicate any potential errors encountered, right? And to motivate this for next time, I will recall, here's the motivation, right? Suppose you wanted to write a function to compute the roots of a quadratic equation. Or, more relatably, tomorrow in your lab, you will write a function, a series of functions, to take a pixel and discolor it. There are several ways that you can discolor things, like take an image. Each one of those pixels, you can convert it to a black and white pixel, so that you can take an entire image, a color image, and create it and convert it to a black and white image. Or you can go fancy and you can go sepia tones, right? Sepia tone, well, the color in every pixel has 3 values, an R, a G, and a B. That's red, green, and blue coloration. If you want to create a function to return those 3 values, I'm going to take this pixel, RGB, I'm going to convert it into sepia into these 3 values and return those 3 values back to you, RGB. I can't do that directly unless I start using pointers. Instead, I have to write a function for red, a function for green, and a function for blue. Why write 3 functions that that are all related? Just write one function and return these 3 values as parameters instead. You won't do that directly next week, tomorrow in lab. You'll get started. We don't assume pointers in lab 5. Instead, that's lab 6. But then you'll come back and redo it so that these are all passed by reference. Okay? We'll go ahead and get some more practice next time as we start talking about error codes, basically. So suppose that you wanted to write a function to compute roots of a quadratic equation, root 1 and root 2. Ultimately, what we have to do is we have to write 2 functions. Without pointers, you have to write 2 functions, right? 1 for each root. And we'll go through that process on Wednesday. Any questions? No? All right, I'll see you on Wednesday. Have a good lab 5 tomorrow. There we go.